So the thing is to talk about some questions about manifold with positive scalar curvature, which have been raised recently. And I will try, since it's supposed to be a wide audience talk, to give at least informal definitions of all the things which are involved in the talk. And the objects of Riemannian geometry can be a bit hard to grasp at first, so I'll do my best. Okay, so first, let's try to see what scalar curvature is. So first, let's start with a Riemannian manifold. So let's recall that on a Riemannian manifold, you have the metric G, which is an inner product on each tangent space. And with that, on each tangent space, so on tangent spaces, and so with that, you can measure the speed of a curve inside your manifold. So, and with that, you can measure the length of curves. And once you can measure the length of curves, you can put a metric space structure on Mn, which is called the Riemannian distance. So what is the distance between 2 points in M? So this is the infimum of the length of curves, such that so gamma is a smooth curve, let's say from 0, 1 to M. Gamma of 0 is X, gamma of 1 is Y. So, and this is, for instance, this is what you, a natural example of Riemannian manifold is, let's say, an hypersurface defined by a nice equation in Rn plus 1. Then you can measure the length of curves on that, and you will get a Riemannian manifold like that. And so, just like curves in the plane, Riemannian manifold have curvature. And one of the difficulty of the topic is that they have many different curvatures. But the general principle is that if you have big curvature, then you tend to be small in some sense. So, for instance, maybe let's take a very small, very basic example. So if you have a curve in R2, let's say a convex curve. So then the curvature is the inverse at each point of the curve of the circle which approximates the curve in the best possible way among all circles. And so if this curvature is very big, so if each of those circles is very small, then your curvature will be small. Basically, if the curvature is bigger than 1 over r, then your curve can be put inside a disk of radius r. So big curvature, small geometric objects. And there's many incarnations of this principle. So first so there is some kind of curvature, which is called the Ricci curvature, which is a very famous object. And for this notion, like if the Ricci curvature is bigger than n minus 1g, so why this? So this is what it is for the sphere of dimension n, like set of x in Rn such that the norm of x is equal to 1, really the round radius 1 sphere. So if the Ricci curvature is bigger than the Ricci curvature of the sphere, then there are several implications. I will just put 2 of them here. The diameter as a metric space of your manifold is less than pi. This is called Meyer's theorem. And pi is the diameter of the sphere, like intrinsic diameter. So what is the shortest path to go from the North Pole to the South Pole? It's to take a meridian, and it's of length pi. And so this is some kind of geometric smallness. And from that, you can actually deduce a topological corollary, which is that the fundamental group of the manifold is finite. Basically, if you've done a little bit of topologies, because so this conclusion on the diameter will hold also for the universal cover of M. And so the universal cover will be something which has finite diameter, and manifolds are, so you have, yeah, I forgot about something. So we will assume the manifold is complete as a metric space, which has a nice trajection on geodesics, which make that there's a geodesic equation, and you can follow a geodesic curve as long as you want. You want so that prevents some kind of holes in your manifold. Okay. So yeah, then once you have this metric version of Meyer's theorem, so the universal cover of your manifold is also compact, so that gives you that the fundamental group, the pi 1 here, is finite. So this is a topo. So this is once again saying that your manifold cannot be too big, but in a topological sense. So this is topological smallness in some sense. And if you replace the Ricci curvature by other curvatures, for example, the sectional curvature, you will have the same kind of result, but with maybe stronger implication for sectional curvature. But usually in Riemannian geometry, when you have big curvature, you have a small manifold. And this is a big theme, either in a geometric sense or in a topological sense. But let's turn to the scalar curvature. So maybe the Ricci curvature is already a complicated beast, because it's a curvature which depends on one point in the manifold and a tangent direction. It's a quadratic form on the tangent space. So, or you can see that, let's say, the symmetric matrix at each point of your manifold, which you compute using partial derivatives of the metric and so on. So it's already quite complicated. So maybe we want to have, like for curves in the plane, or even for surfaces, some simpler notion of curvature. And so one way to do that is to look at the scalar curvature. And the scalar curvature is, as the name suggests, just a scalar. So you take a point x in your manifold, and it will spit out a number, a real number. Okay, and one way to say that is to look in terms of volume. So maybe if we want to be quick, so when you have a Riemannian manifold, you have a metric space structure. And actually, so with this metric space structure, you can define the Hausdorff measure and a Hausdorff dimension. The Hausdorff dimension will be the topological dimension of your manifold, it will be n. And so we can compute volume of balls. We have a distance, we can compute balls and volume of balls. And we can try to relate the volume of a ball of radius r in a manifold of dimension n with the volume of a ball of radius r in just standard Euclidean space of dimension n. And you can try to compute an expansion in terms of the radius, and it will look like that. So at the leading term, the leading term will be just this, the volume of the ball in Euclidean space. And then you will have, I think my tablet froze now. Does it move?
Wait, it moves.
Oh, okay.
I can see when you. Yeah.
Yeah. Okay.
Yeah,
No. It was my. Yeah, on my computer it didn't move, so I wasn't sure you could follow stuff. Okay, so you take a ball of small radius r. It will have in your manifold. It will have the same volume as in the Euclidean case for small r, up to a small correction term. And this correction will be up to some dimensional constant, r squared times the scalar curvature. This is one possible definition of the scalar curvature. It's not the most convenient one for calculations, because you need to know balls, and if you need to know balls, you need to know the distance. And to compute the distance as the infimum of the length of curves, as here, usually involves solving nonlinear second order ODEs. So yeah, but there is a more practical expression in terms of the partial derivatives, second order partial derivatives of the metric. So of this symmetric matrix, and you compute partial derivatives and Laplacians, and so and it will give you this curvature. But this is a more geometric definition. So what can we do with that definition? So, well, on our end, this expansion is exact. So there's no correction term. So the scalar curvature is 0. Okay, boring. What about the sphere? Okay, so on the sphere, when you travel from, let's say, the North Pole to radius r, the sphere of radius r, inside the sphere is a sphere of radius sine r inside the ambient space of dimension n+1. Okay, so just picture that, like if you take a parallel around the North Pole, it's smaller than what it is if you like try to unfold the whole sphere. And so if you want to compute the volume of a ball of radius r in the sphere of dimension n, you will get, so you will just integrate the size of all these spheres, and so you get that thing. So volume of the sphere of dimension 1 less, and some integral of some power of the sine function. And then you can like write sine t to be t minus t cube over 6 plus some other stuff, and try to integrate that term by term, and you will get this expansion for small r. And yeah, so this is the volume of the ball of radius r in the sphere, in the Euclidean space. And so in the end, you compute the scalar curvature. So the scalar curvature of the sphere of radius r is n minus 1. Okay. Now maybe for surfaces, I don't know if you've thought about surfaces recently. So there's a notion of curvature which is Gauss curvature, and the scalar curvature for surfaces is just twice the Gauss curvature. So what is the Gauss curvature? You can see it in the, well, you could define it with this volume of disk, but there is a more traditional approach, which is like you take your patch of surface, okay, like that, maybe. Let's take some kind of saddle point. Then you consider a normal vector. here. And if you want to take the most geometric possible definition, you take some planes containing the normal vector. So the section of sigma with this of your surface sigma with this green plane will be a curve in a plane, so it will have a curvature. And when you rotate your curve around your plane inside around your normal, then this curve will change, and its curvature at that point as a plane curve will change, and it will go. So this was a result by Euler. It will go from a minimum to a maximum, and the product of this minimum and this maximum is the Gaussian curvature. So here you see that the curve change orientation if I have a saddle point, so it will be something with negative curvature, whereas if you are on a convex surface, all the curves will have the same orientation and this will be positive curvature. And so this curvature, as I defined it, as a product of those maximal and minimal curvature, it's called the Gauss curvature, and scalar curvature is related to that, which is not obvious actually. It's already quite some work to link both those point of view. Okay, so this first definition kind of tells you that if you have big scalar curvature, then your balls will be significantly smaller than what they are in the Euclidean space in some sense. However, it's only in the infinitesimal sense. You cannot, so this is really an expansion for r going to 0. It will not tell you that for, I don't know, r equal 10 to the power n minus 6, 10 to the power minus 6, your ball will have a definite defect from in volume from the Euclidean case. So you cannot really integrate this asymptotic expansion for r small. Actually, and this is a huge help, when you have Ricci curvature bigger than something, you can get inequalities for the volume of balls of any radius. But with scalar curvature, it's really only in an infinitesimal sense. You cannot directly get macroscopic information from this expansion. Okay. So yeah, so this is only an infinitesimal result. There's no estimate on the volume of balls, for instance, at a definite scale. And so now what computational properties does that have? The scalar curvature. So here I assume that my manifold M is a product of two manifolds M1 and M2 of smaller dimension, each coming with a metric. And then, so the scalar product of the scalar curvature of the product, it's just the sum of the scalar curvature. Another result is that if you have two, so this is to give us a wide range of examples. So assume now that you have two manifolds of the same dimension. Maybe so M1 and M2, and assume that they have a scalar curvature greater than some lower bound S that you see here. Then the connected sum of both, which I will recall afterwards, will also have a metric with the same lower bound on the scalar curvature. So yeah, maybe let's make a picture here. So let's say you have M1 here, So you have M2 here. What is the connected sum? The connected sum is built in the following way. So you pick 2 points wherever you want on M1 and M2. You remove small balls around each of these points, and you glue, by making some kind of tunnel, those points together. So for instance, this is how you go from 2 donuts to a donut with 2 holes, stuff like that. Okay, this is that topological construction. And
Sorry,
you can
Tom, are you drawing something? Because,
yeah, okay, so now we are okay, no, I think it came back.
Yeah.
Okay,
yes. And also I have what's the notation like DS?
sharp, yeah.
Sharp?
Yeah.
Well,
like
it
in
means
music.
that they are different.
What?
What's the meaning of the sharp?
This is the connected sum. Oh yeah, maybe I should have written that. This is not that standard. So here, connected sum. This is what I'm explaining right now. Okay,
Sorry.
so the connected sum is that you take M1 and M2, you remove a small ball, 2 small balls on each side, and you glue them with some kind of tunnel. So, and you can do that without disturbing the manifold too much. So in fact, it's possible to do that by keeping the metric exactly the same here, and you can make the tunnel with a scalar curvature greater than S. And so you manage to glue stuff together. And that tells you some interesting stuff. For instance, positive scalar curvature. So usually when I'm interested in strictly positive scalar curvature, I will assume that it's greater than n minus 1 because I compare to what's going on in the sphere. That's why. I could have taken 1, but then traditionally you compare with the sphere because the sphere is a very nice manifold with constant curvature. So that tells you that, so those 2 examples tells you that positive scalar curvature cannot control pi1, so the fundamental group. So why is that? So for pi1, you can see that in that way. So there's a null result by a topologist which says any pi1, any group any G is finitely presented, actually, is the pi1 of some compact manifold of dimension 4. Okay, so you can put using partition of unity, you can put some metric of dimension, some Riemannian metric on X4, and then you can look at a new manifold which would be M6, which would be X4 times the sphere of radius epsilon. Then the scalar curvature of M will be the scalar curvature of X. So then S2 is simply connected, so pi1 of M is equal to pi1 of X is equal to G. And the scalar curvature of M will be the scalar curvature of X plus the scalar curvature of a sphere of radius epsilon, and this is 2 over epsilon squared. So since X is compact, you can make that, you can make this scalar curvature as big as you want, as long as you take a small enough sphere for the second factor. So you cannot get control on the fundamental group from a lower bound on the scalar curvature. Whereas for Ricci curvature, in fact, it was, we knew that the fundamental group was finite. So this is not that great. And so this is using the first formula for the scalar curvature of a product. But then we also have with this connected sum construction, we can also see that there is no control on the diameter or the volume in this way. So you start with any m, and then I can make like a connected sum with, I don't know, maybe a sphere. And I can continue this process, and I can like ensure that these guys don't shrink, and also that the guy that I'm adding don't shrink. So, and I can make this connected sum as long as I want. So, and I can get a metric space of diameter as big as I want, and the volume also can be as big as I want. So there's no control on the pi1, on the fundamental group, no control on the diameter, and no control on the volume. However, the topology cannot be too complicated, and this was proven by Shen and Yao and Gromov Lawson in the 80s, late 70s, beginning of the 80s. The torus Tn, so what is Tn? Tn is just a product of circles. So it's S1 to the power n. Usually we call that S1t, and so this is Tn. And Tn doesn't admit a metric with positive scalar curvature. We'll see one way to prove it at the end of the talk. Okay, so this is really, so we are going in the good direction. So the manifold cannot be too big from a topology point of view. So Tn has a lot of topology, and it cannot have positive scalar curvature. Okay, so now maybe since the seminar is supposed to be about mathematics and theoretical physics, let's make a small detour in things with physical meaning. And so I will talk a little bit about scalar curvature and general relativity. So in general relativity, space-time is described by a Lorentzian manifold which satisfies Einstein equation. So this is almost like a Riemannian manifold, except that there is a somehow preferred overall direction of time. And so instead of having a Riemannian metric on each tangent space, you have a Lorentzian metric, which is something like in special relativity. So something like minus dt2 plus dx squared plus dy squared plus dz squared. So a quadratic form of signature 1, 3 or 3, 1. And so inside this space-time, you have, and this space-time is supposed to satisfy Einstein equation, which is something which can be written in terms of curvature. Inside that, you can take like time slices, you freeze time, and you have a 3 manifold with a Riemannian metric G. Okay, and there are physical assumptions which are natural on those time slices, and the thing that you can assume is that G looks like Euclidean space when you're far away. And this models an isolated system. So how do you write that? Well, you assume that outside of a compact set, your manifold is just R3 minus some ball. And so Gij is just a coefficient of your metric, as a symmetric matrix. And it's delta ij plus something which decayed at that rate. And then you ask something about the first and second derivative. So this is a model of isolated system. Like far away, it looks like empty space, which is just R3. And there's another natural physical assumption, which is this one, which is called the dominant energy condition, and which is something which tells you that forces and fields cannot travel faster than light. Okay, but anyway, so this gives like natural condition on the geometry of this this time slice here. And there you can define something which is called the ADM mass. And it's defined like that. Some integral on bigger and bigger sphere. This is more or less a reminder of like a Gauss theorem in electromagnetism. Like if you take the, might get that wrong, but if you take the flux integral of the electric field on a sphere, you will get the electric charges which are inside the ball, and so you're more or less trying to mimic that with some kind of gravitational field for a Lorentzian manifold. And once again, Shen and Yao, beginning of the 80s, and this was a big theorem actually. So if you have a string manifold which is asymptotically flat and where the scalar curvature is bigger than 0, then this ADM mass is positive. So it was a big mathematical theorem to prove that in a general relativity, a physically meaningful system cannot carry a negative amount of mass. This is already a very difficult theorem, which I find very amazing. And then 20 years later, there has been a quantitative version of that, which will give us an insight on some other stuff, which is called the Penrose inequality. And so what is this Penrose inequality? It tells you, it gives you not only that the mass is positive, but it gives you a lower bound and a quantitative lower bound depending on the geometry of your manifold of this mass. So what is that? So that tells you, so same hypothesis, and then it will tell you that, so yeah, maybe there is something there. There's some kind of boundary here, and this is more or less the event horizon of a black hole. And so this is a surface in 3 dimensions. It's a minimal surface. We will explain what it is in a few minutes. But this is also called the Hawking mass of the black hole sigma. And so once again, a difficult theorem in mathematical general relativity is that the global mass of your manifold is bigger than the mass of one black hole inside your manifold. This is already difficult. Yeah. General relativity is a very complicated physical theory. Like anything which you can say which is physically meaningful is usually complicated to prove in a formal sense. Okay, and so that gives us some kind of quantitative implication of scalar curvature, and we will see, like using minimal surfaces, how we can get some other one. Okay, so now maybe something about minimal surface or hypersurfaces. So I'm once again in a manifold of dimension n, and I take sigma some submanifold of dimension n-1. We call that an hypersurface. And nu here in green is a normal vector field to my manifold.
Thomas, there is a question in the chat.
Ah, okay, sure. I see. Well, I don't know. Like I have MADM bigger than MH, so MADM minus MH will be bigger than 0. Was that the meaning of your question?
Is it bigger if we remove the mass of the singularity?
So if I remove MH for MADM, I will get that the difference is bigger than 0. That's the content of the theorem. Did I understand your question right? Okay. I'm not a big expert in general relativity, but since there was physics in the description of the seminar, I thought it was interesting to make this link. Okay, so now let's talk a little bit about minimal hypersurface. So let's try to understand what's going on if I wiggle a little bit my hypersurface. So f will be some function from sigma to r, and then I will move a little bit my my manifold here to get some sigma t, and I will move it in the normal bad direction by f of x. So that's what I mean by this equality. So assume that you're in Euclidean space or in something where that makes sense. There's a you need to be a little bit more careful in manifolds, but that's not a big deal. So, and I can look at the area or the n-1 dimensional volume. Let's call that the area. And I can compute the area of this one parameter family of hypersurfaces, and I can take the time derivative of that at t equals 0. And I will get some kind of formula, whereas this is some kind of curvature, which is called the mean curvature. And so an example of bad terminology that sticks is if this derivative is 0, so for any deformation, so for any f, that means that this curvature is 0, and we call that a minimal hypersurface. In Euclidean space, it models soap films. Okay. But it doesn't need to be minimizing in the minimum of anything in that way. It's just like critical point. But we can also compute the second derivative of the area. We get some maybe not so nice formula. But if this second derivative is non-negative, in particular if we are at a minimum of the area among, let's say, all hypersurfaces of some kind, then we call that hypersurfaces surface a stable minimal surface. Okay. And this is useful because when we compute this second variation formula, so the scalar curvature of M and the scalar curvature of the minimal surface appear. So that will give us some information. So let's see how we can use that. Okay. Okay, so let's see how we can prove with that T3 has no metric with positive scalar curvature. So let's assume that I have T3 with some metric G with positive scalar curvature, and I can look at T2 times 1 point, so this is a torus T2 inside T3, and I can deform that to minimize area. So it will give me a new surface. In some sense, sigma 2 will look like a torus topologically. And it will be a stable minimal surface. So this second variation is non-negative if I have a minimal surface. So for any f, so from sigma to r, integral of gradient f squared minus 1/2 scalar curvature of m minus scalar curvature of sigma plus or minus plus second fundamental form squared f squared d sigma. This is bigger than 0. Now I can plug f equal to 1 there. So gradient f goes away, so I get that minus 1/2 integral of Sm minus S sigma plus A squared. So integral of a sigma. D sigma is bigger than 0. I can remove this pesky 1/2 here. So this will be less than 0. And then, so I can put S sigma on the other side. And not integral over M, over sigma. Sigma, I said. And so sigma is a torus. And in dimension 2, so we said that in dimension 2, the scalar curvature is twice the Gauss curvature. And then there is a theorem which is called the Gauss-Bonnet formula, which tells you that the integral of the curvature of a compact surface is the Euler-Poincaré characteristic, which is 0 for the torus. And so we have 0 bigger than 0, so we have a contradiction. Yeah. So here, since this is bigger than 0, we have something which is strictly positive. And here. Okay. So we have proved there that T3 does not have any metric with positive scalar curvature. Okay, but we are still in the realm of topology. So this is a topological, this is not a quantitative result. So maybe let's try to prove this in a quantitative way. Okay, I have 15 minutes left. So before going with the proof, maybe let's try to build a counterexample, okay? So let's try to build a metric with strictly positive, let's say more scalar curvature than the sphere on the torus of dimension n. So I will start with the torus of dimension n minus 1, and like with the flat metric, by that I mean like you take for instance Rn minus 1, and you can quotient it by the lattice Zn minus 1 with just a flat torus. So this has 0 curvature. And then I will try to do what is called a warp product construction, where I add a direction, let's call it T. I add a T dimension, and then I will try to change the size of my torus here in such a way that the curvature is positive. Okay, so this will give you a metric of this form, and you can compute its curvature. The scalar curvature then is, so f is just a function of one variable, and it's just that, like f, some second derivative and first derivative, and f itself. So, and if you want, so okay, maybe there's no need to do too much stuff. Let's try to get exactly n times n minus 1 curvature. And so this gives you an ODE on f, and you can more or less solve it to translation, and that will give you that. But what does it tell you on your f? So f was cosine of something to some power. So basically it was going like that. And the problem here is that, so a Riemannian metric is a positive definite quadratic formula. So if this goes to 0 at some point, then it's not a Riemannian metric anymore. So you have singularities, you have lost dimensions in some sense. So we cannot, because so we won't be able to glue that back together to get a metric on the torus. If we had found something which was nice, which was like that, for instance, at some point we could have closed that and get a metric of the torus. But you know, you see it never goes in the right direction for us to be able to do that. Okay. So we cannot build a flat metric with positive scalar curvature on the torus in this way. And actually there's something deeper in this example, and this was uncovered by Gromov a couple of years ago. So now I take any metric on, like, in this situation, like a torus time an interval. And I take n less than 7 because of a PDE reason. Maybe I'll tell you afterwards. And I assume that on this manifold with boundary, the curvature is bigger than n minus 1. Then the two boundary, yeah, maybe let's make a pictures. So assume that you have Tn minus 1 at each end, and that you fill it here by a metric on the product where the scalar curvature is bigger than something. Then
Thomas, actually the same we can say what you are drawing.
Okay.
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 Yeah, perfect.
Then the two boundary components here are separated by a distance of less than 2 pi over n. They cannot be too far away. And the optimal case is just the example we built before. And so this is a quantitative implication, but you see that it's kind of a trade-off. We see that scalar curvature cannot control topology alone. It cannot control geometry alone. But here we have a trade-off. If the topology is complicated enough, not too complicated to allow for positive scalar curvature, but not too simple, then we can get some quantitative results. Okay, and in the last 10 minutes, I think I'll tell you how this is proved, and I guess we'll be done afterwards. Okay, so first we'll do a computation. So we start with a manifold sigma of dimension n, or n minus 1 actually, with a Riemannian metric H. And then I will build a new manifold, sigma times S1, so S1 is the circle, in the following way. At each point, x, in sigma, I will attach a circle of radius f of x. And so the size of the circle I attach depend on the point on sigma. So that gives you a Riemannian metric of this form. So in the h direction, in the sigma direction, it's just the original metric h. And I add d theta, which is like a coordinate on my circles, but I stretch it by a factor of f. Okay? And then it's a computation that the scalar curvature of this new metric is the scalar curvature of sigma minus twice Laplacian f over f. So there's a calculus of Riemannian manifold, there's a Laplacian. It's not too complicated. And then I will use this construction to make a symmetrization argument. So it goes in this way. So in green here, I have minus 1, 1 times Tn minus 1 with the metric G. And sigma here, so inside this, inside this minus 1, 1 times Tn minus 1, I can build, can consider this hypersurface times 1 point. Basically, I just look at the slice by one of the coordinates if you want. I make I consider this as the last coordinate. I call that, I don't know, theta n minus 1. And I look at theta n minus 1 equals some constant, and all the rest is free to move. And so this gives me some hypersurface. This hypersurface, so yeah, this will be my sigma. Let's say maybe it's, so it will be, let's say, this one. Among all the deformation of this hypersurface, I can find some sigma which minimize area. It will have topology not too different from the original topology, okay? And it will be...
one question. When you say deformation, you mean what we are changing exactly?
Actually, the proper setting to look is to look at inside the homology class with fixed boundary component, or with no, a free boundary. Yeah.
Okay.
And you use geometric measure theory to get that you can minimize, like you have a functional which is lower semi-continuous and stuff like that. It's quite technical.
Okay.
And this is where this n less than 7 comes from. Because this minimizer will be a smooth hypersurface only in dimension up to 7. Starting in dimension 8, there are counterexamples. Okay. And so this is stable. So what was stability? What did it give us? Give us like positivity of this quadratic form. And this is a, like, how is it called? This is a Schrödinger operator, more or less. So this gives you that this operator is positive, okay? So for any f from this sigma to R. So I can take its first eigenfunction by just minimizing this. And so it will be positive because it's the first eigenfunction of a Schrödinger operator. And it will satisfy this with some positive first eigenvalue. Okay. And now I will make the following construction. So I will keep sigma, I will remove m. Okay, bye. I just keep sigma, and now above each of this stuff, each x in sigma, I add a circle of radius f1 of x. Just the construction I made before. So this is my new, so this new manifold, I call that mg twiddle. And so this is sigma times S1 with a metric of the form I described before. Okay. And so by the observation we made, the scalar curvature of G twiddle is S sigma minus this 2 Laplacian blah 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 blah. Okay, but let's maybe let's try to take advantage of that. So what is L? So lambda 1 F1 is L sigma. Oh, sorry. So lambda 1, maybe let's take another color. Lambda 1 F1 is L F1, And so what is LF1? So it's minus Laplace F1 minus 1/2 some term which did have, so scalar curvature of M minus scalar curvature of sigma plus this positive term which is of geometric nature times F1. Okay, it's just writing that this is the first eigenfunction. So now I can write that as S sigma plus, because I will have Laplacian of F sigma, 2 lambda 1. No. Yes? Yes. 2 lambda 1 plus 1/2. No, the 1/2 goes away because of the 2. Sm minus S sigma plus A squared. Okay? This is just an explicit computation using those two formulas. And then we're in luck because the S sigma goes away. And so this is equal to 2 lambda 1 plus Sm plus A squared. Which is, so lambda 1 is positive, so this is greater than Sm, which by assumption was greater than Nn minus 1. So basically we've replaced our original manifold by this one. So what did we gain? We gain a symmetry because I can turn around those circles that I added. So there's a group action by the reals here. And so that gives me a new symmetry. So basically I've reduced the dimension of the problem. So this d theta, if I replace theta by theta plus theta naught, the metric doesn't change. So this is an isometry of my manifold. And I can continue to play that game with the remaining coordinates. So I was playing with fixing theta n. Now I can fix another theta and so on. And in the end, I get this, a metric of this form, which has a lot of symmetries, like you can translate each of the theta I. And I won't have changed SG. And what's more important is that the distance between the boundary component can only increase when I'm doing that, because going from the two boundary component in the green manifold is always less expensive than being constrained to go from the two boundary component in the red manifold, because you have more paths to follow in the green one than in the red one. So it goes in the right direction with respect to this thing that we want to control. And so in the end, scalar curvature greater than Nn minus 1 give you this differential inequality, and then you do some Cauchy-Schwarz and integration and stuff, and you show that Fi cannot be defined on an interval of length more than 2 pi over n. Just maybe you can put that as a homework for a differential equations lecture that you give one day. Okay, maybe some other stuff that we can control. Using similar methods, you can, yeah, maybe just, maybe I can give you, yeah, I guess. Yeah, maybe one extra result by Gromov. Okay, I just copy paste the statement. Okay. Okay. Oh, excuse my French. So assume that you have a metric on the cube, just -1 times to the power n. So you have your metric on a cube here, which has positive scalar curvature. And di is the distance between each pair of opposite faces. So this would be like d1 like that, d2 like that, and d3 like that. Okay. Then you have this inequality, which tells you that.
Thomas, sorry, we can't see what you are drawing. Again, please.
Okay. Usually it comes back. Oh. Okay, maybe just. Okay. So basically, di is the distance between those faces, and if you have positive curvature inside your cube, then minimum of the di is bounded above. So there is a direction in which your cube is small. It cannot be big in all directions. There is a direction where it is small. And this is pretty quantitative. And you can also relate those that positive scalar curvature with the size of two spheres inside like positive inside some other manifold. Okay, maybe let's maybe I'll stop there. Thank you for your attention and your questions.
Okay, thank you, Thomas, for the clarity of the talk. So let us open the floor for questions. If you have any question about on subject of talk. So I guess I will start first. So it's just concerning the last two theorem. Our objective is to attain some quantitative results on the if we have an upper bound on the scalar curvature. So the first one was on the torus, and this one, the second one, is on the cube. So I'm just asking if there is other like manifolds on which we can say something about this kind of.
Yeah, maybe the one of the easy one is so S2 times S1, the three manifold with scalar curvature greater than here the comparison is 2. Then there exists sigma, which looks like S2 times a point with area at most 4 pi. So basically, so the model here would be like round S2 with scalar curvature 2 times flat S1. Here, any sphere like S2 times a point has area 4 pi. And so if you're more curved than that model, then there is one sphere which has area at most 4 pi. And so yeah, and you can put like you can replace here S1 with Tn, and it also works. And you can also look at S2 times R2, it works, and it's a work in progress to find something optimal in S2 times S2.
Okay, I see. There is a question in the chat.
I'm reading it, yeah.
Yes.
Okay, so when you minimize n-1 dimensional area inside an n manifold, then there is a big regularity result which will tell you that you will get something smooth. And actually, in general dimension, you will have singularities of codimension 8. And there are explicit examples. So, but in higher dimension or in higher codimension, like if you try to minimize the surface of something of something of dimension 2 inside the 4 manifold, there will be singularity also. The problem is not to actually the presence of singularity is not so much linked with minimization. They will appear, and it's not too bad. Like the surface, singular surface you will get will be minimizing in the sense of currents, Federer and so on. And but the thing is that to make this computation work, like with Laplacian on the surface and stuff like that, then if you have singularities, it's complicated. Actually, Shane and Yao have been claiming since the mid-80s that they do have a way to circumvent the singularities in higher dimension, starting in dimension 8 and more. But it's still, after 30 years, it still haven't been published. But if it's recorded, maybe I shouldn't say that in that way. But there are preprints and people trying to understand them, but so far it's not clear.
For the sorry, I don't know if there is other question.
I have a question.
Yes.
Yeah. It is about, I mean, a possibility to extend these kind of results in the context of graphs. So I know that people started to think about notions of Ricci curvature, of scalar curvature, and so on, Olivier Ricci curvature, and so on. But would it be meaningful to have this kind of approach in the context of graphs? And what do you expect about this?
Yeah, I know that there are notions of Ricci curvature for graphs which work well. But here, yeah, for instance, I guess that the first bound I gave on the, so those are based on optimal transport, no? Are they?
Yeah, usually, yeah.
I guess that this first result, like on the diameter, you should probably get that with the notion of positive curvature by Olivier Benoit. But scalar curvature in that case, well, going with the volume won't help because there's not really a model. Actually, it's not even so. More generally than graphs, it's a very big problem to have a notion of scalar curvature which makes sense on singular metric spaces and so on. And it's still very much a work in progress. And most of the approach are very continuous in nature. So, and I guess that applying them to combinatorial objects is not clear.
Okay, thank you. Thank you.
So Is there any other question? I was just wondering, yeah, if for the theorem, this one, we use like the same. There is symmetrization in the proof. I mean, we use this idea of symmetrization in the proof of.
Yeah, in a more delicate way. You have to. The problem with that kind of stuff, like here, so here we were minimizing, so the surface didn't, so we were minimizing for stuff like the blue stuff, so it was constrained to touch each boundary, so it couldn't disappear, like going out in one boundary component to infinity and stuff like that. So we had good compactness properties on those stuff. Here, in the case of the cube, like you would like to minimize stuff on hypersurfaces that look like that, for instance. And it's unclear that if you try to minimize stuff, it will just go to the boundary and disappear, and so you're screwed if that's the case. So you need to change the notion of area and to penalize it so that it's not interesting it avoids the boundaries, stuff like that. And there's a clever way which is called the mu bubbles by Gromov, which will ensure that, like that you can find something which stays inside. And this is so minimal surface is h equals 0, and these mu bubbles is h equals something. So you go from 0 mean curvature to a problem of prescribed mean curvature in that case. But you change a little bit the functional, and it will. So maybe another way of explaining that is that, so when you look at our example here, so we are the stable minimal surface that we use are going like from there to there, and so they do have boundary, okay? And we don't like boundary. Boundary are complicated to deal with, so we prefer not to have boundary. And there's a minimal surface right here, right in the middle here, but it's not stable because if you push it in this direction, the volume decreases. The idea of Gromov is to change the functional by something which depends on this coordinate, so that instead of the area, you look at the area plus some correction term, which will make that guy stable. And so it will help you not to be too bothered with boundary problems.
Okay. Okay. Thank you for the answer. So if there is no other question, let us thank our speaker. And so the next seminar will be in 2 weeks. So thank you for, I don't know if you have any comment, Eda, Mathieu, to add. So if
I thank, of course, I thank Thomas for being here, for this very nice talk, and
Yeah, thank you so much.
Thank you.
So thank you for all the attendee, and see you in the next talk. Have a good day.
Okay.
Okay.
Thank you, Othman. Right.